Okay, so good afternoon again to those who were here before. Can you hear me? Anybody in the chat? Do you hear me? Okay. Okay, you should also see the screen. So let's get to this laboratory, which is laboratory 5. You guess, if you ask what happened to laboratory 4, if you check online, laboratory 4 is on clustering. It is only for the 01HERU people. I keep consistent numbering because otherwise you will get a mess, but for you there is no laboratory 4. We just get to laboratory 5. Of course, if you want to look at the clustering, you have it online. Now, laboratory 5 will focus on what we discussed last week and we ended up seeing yesterday. Maximum multivariate Gaussian densities and their maximum likelihood estimates. It's divided into two parts. The first will deal with the density, and the second part with maximum likelihood estimates. Now, the first part will require to write functions that compute the multivariate Gaussian density. We have seen the definition of the density in class. We have seen it also again today. What we want to do is to write a function that computes the density. Or, to be more precise, we have discussed why working with the density directly may be a problem. We have said that we have exponential. Well, it's a problem where when we want to compute the likelihood, because the likelihood will be a product of densities computed for samples. If the density values are smaller than 1 and I multiply lots of them, I will underflow and get a value of 0. But even computing the density for a single sample, if the sample is large dimensional, may be problematic. Imagine that you have covariance matrix equal to identity and a vector x which has all components that are small. Why? Because, for example, this represents pixel intensities as floating point values. Now, what is a Gaussian density for computer at this point? Well, its exponent is some constant here times exponential of minus 1/2 x transpose x if sigma is identity, which is exponential of minus 1/2 the square norm of x. But the square norm of x is the sum of, sorry, it's the opposite. My mistake. Let's imagine that you have features that represent, for example, the pixel intensity, but as value between 0 and 255. Otherwise, it doesn't work. So I have pixel intensities that are integers. It's the square exponential of minus 1/2 the square norm of x. But the square norm of x is what? It's the sum of the square of these values. So it will be a very large value. If the square norm of x is large, exponential of minus 1/2 the square norm of x will quickly go towards 0. So I will end up again with issues where I underflow my computations. So to avoid this kind of issues, it's better if we look at the logarithm of the density. In this case, I would have just the norm, the square norm here term, which would not underflow. The logarithm of the density has this expression. First step, compute a function that given a sample x as a column vector, so m times 1. The mean mu as again as a column vector, m times 1. And the covariance matrix sigma, this will be m times m, or we call it C in the code for covariance. In the text is sigma, but we can't use sigma as variable in the code. So we'll typically use C for the covariance sigma and P for the precision lambda in the code. In any case, given these three values, computes the log density for x given mu and sigma. So this expression. How do we do this? Well, we use some existing functions. These inv functions can be used to compute c minus 1, that is the precision, that is lambda. C is equal to sigma. And then we need to compute the log determinant of 1/2 log determinant of sigma. Actually, it's the logarithm of the absolute value of the determinant of sigma, but since sigma is, we assume it's positive definite, so all the eigenvalues are greater than 0. This is not greater. This is this symbol, which means positive definite. Actually, written correctly, it's like this. It's not a greater than. It means that all the eigenvalues of sigma are greater than 0. Then the absolute value of the determinant will also be this time greater than 0. So we don't, and also the determinant of sigma will be greater than 0. So whether we take absolute value or not doesn't matter. But we still need to compute the determinant of sigma. Again, here we leave the logarithm of the determinant. But if we were to compute first the determinant and then the logarithm, we would end up with a similar problem. Imagine the sigma is a covariance matrix that has all variances equal to 2, but is very large. The determinant, imagine that this is diagonal for simplicity. So a diagonal covariance matrix with all diagonal elements equal to 2 means a covariance matrix where the variance of each feature is 2. It's not unreasonable. But now imagine that this is 1000 by 1000. My determinant is 2 to the power 1000, which I can't compute. But I can compute its logarithm. That's 1000 the logarithm of 2, which is something that I can compute in practice. How do we do this computation? For a generic matrix, we have this slogdet function that computes the sign and the logarithm of the absolute value of the determinant of a function. The absolute value is the second thing that it returns. The first is the sign that for us will be 1 because the covariance matrix is positive. So we will call this function, and this will compute in a robust way the values of C. Actually, if you want to know how it does it through a decomposition similar to the eigenvalue, to the decomposition of sigma that allows me to compute the determinant of a matrix. The determinant is the product of the eigenvalues, so if I can compute the eigenvalues and take their logarithm, then the log determinant is the sum of the logarithm of the eigenvalues of the matrix. So I can compute it without computing the determinant at all. Write the function that does these computations. Then, in the future, we will typically need to compute the Gaussian density for a set of samples. So if we have a matrix of samples like the iris dataset, we will have n samples, n equal 150 for the iris. We will want to compute the density for all these samples. Now, we do this by writing a function, by extending the function nd so that it receives a data matrix, and if you pass an array, it will return the density. If you pass a matrix which contains more than one column, we'll build an array that contains all the densities of the corresponding sample. So if I pass an array which contains a matrix which contains x1, x2, x3, the function should give me an array which is logarithm of x1, logarithm of the density of x1, logarithm of the density of x2, etc. in a one-dimensional form, so an array with one dimension. Now, how do we do this? Pay attention, and how you do this will influence heavily your computations. A very naive way would be take the function that computes this expression for one sample and then write a for loop that repeats it for all the columns of the data matrix. Naive solution. Pay attention that the naive solution, you incur the risk of computing the inverse of sigma and the log determinant of sigma several times. But these values do not depend on the value x. So it's not efficient that we recompute it for every sample in the data matrix. So one first optimization could be we compute these terms only once and then Given these terms, we compute only the rest of the terms with a for loop over the data matrix. This will still be quite inefficient but not as inefficient as the first case. Because we have a for loop in Python, we can actually show that we can, and it's what you have online, we can build a faster solution exploiting directly NumPy libraries and NumPy computations. Again, this is something that is a bit harder to get it right, so I will leave it as things that you can try after you have done the naive version of the function. I will explain at the end of the class briefly how it's done, the one that you have online. But again, if you have time, you can try to figure this out. Otherwise, you can stick with the naive. Just pay attention not to recompute unnecessary terms every time. Or you can even do that if you are behind in the laboratory, but know that it will have an impact on the computational cost. Now, once you have written this function, which for the following assumes that you pass a data matrix X and returns a one-dimensional array of log densities, you can try to see if your implementation is correct by comparing it, by using it to visualize the density and comparing it to solutions that you have online for a given set of parameters. The first step is we plot the density of a univariate Gaussian with mean 1 and covariance 2. To do this, we need to call the function that computes the log PDF of the Gaussian, passing as input the samples, the values at which we want to compute the plot, and then the mean and the covariance matrix. Notice that the log PDF density assumes that the input matrix contains column vectors. In this case, what are the column vectors? These are the values at which we want to compute the density as column vectors. So in this case, if I want to compute the density as -7, -6, -5, and so on, I would pass the one-dimensional array that contains these values. This will be interpreted as column vectors, one-dimensional column vectors. For the same reason, we need M to be a 1 times 1 matrix, because mu is 1 times dimensionality of the space, in this case 1, and sigma is M times M, so again 1 times 1 matrix. If you do everything correctly, you should end up with a plot that, if you pass mean 1 and covariance 2, will give this kind of plot. Now, to check that your solution is indeed all correct, you can also check what are the values of the density that you obtain on the y-axis. The y-axis values of the plot are contained also in this file, so you can compute the solution that you get, that is what you plot here, with the PDF that we give you, and check that they are equal up to numerical precision. One thing I didn't say, for the plot, remember that our function computes the log density, so everything here is with log density. In the plot, we want to see the density, so we need to exponentiate the result of the log PDF function. For the plot, we want to see the density itself here. So it's one dimensional, so we don't have issues related to numerical stability. Then, if your function works for one-dimensional data, you can check if it works for n-dimensional data. Here we have a set of samples, a data matrix for which we want to compute the density. We have a given mean and a covariance matrix that we give. So those are the parameters of the Gaussian that you should compute the density for. And this is a vector that contains the log likelihood, the log density for these samples with the parameters given here. So if you call your function passing this data matrix and these parameters, you should obtain these values as log PDF. Again, you can compare that these are similar. This is the plotting and the computation part of the problem. The second part is computing maximum likelihood estimates from a given set of data, and in particular, we will use the XND matrix that you have before as dataset. We want to compute a fit to this data, or the X1D that you have, I will say that in a moment. We want to compute a fit to this data, the maximum likelihood fit. The maximum likelihood is computed after taking the empirical mean and the empirical covariance matrix. This we already know how to do it. So do this for the data in X and D, you will obtain this solution. Are the parameters of the maximum likely fit of a Gaussian model to the data in this data matrix. Then, once we have computed the fit, another thing that is interesting to compute is the log likelihood. Remember that our goal was optimizing the log likelihood. So let's write a function that computes the log likelihood. The log likelihood is what? Is the sum over samples of the logarithm of the density computed at the samples. Remember that if you wrote the log PDF, GAU, and D functions before, that takes a data matrix X and returns a vector Y of log densities. The log likelihood is nothing else than the sum of the values of this array. So if you have done the first part of the laboratory, this should be easy to implement. If you try it with the maximum likelihood solution that you compute on the data X and D, you should obtain this value for the log likelihood. Then you have the same solution for one-dimensional, the same problem for one-dimensional data. Why? Because with one-dimensional data, we can then look at how good is the fit visually. So we have a second dataset with one-dimensional samples, again, as a column vector. So this is a 1 times n matrix, where each column is a 1 times 1 column vector. This represents a single sample. If you compute the maximum likelihood estimate, these are the values that you should obtain. And I actually should write them in this way because these are both 1 times 1 matrices. Then we can use what we computed before, what we did at the first part of the laboratory, and try to plot the density that we have estimated and compare it with the histogram. So we plot the histogram of the data. In this case, we want a one-dimensional array of samples, so we need to ravel it. And then we plot the density over an interval that corresponds to this range with 1000 samples. So as we did in the first part of the laboratory, we plot the density. Again, in this case, we want the density, so we need to exponentiate. For what? For the values that correspond to the x-axis points at which we want to compute the density using the maximum likelihood estimate. This will give us the function, the red plot that gives the function, the density as a function of x when the parameters are the maximum likelihood parameters. And this is what you should obtain as a figure. You can see that the fit is quite good. The shape of the histogram is well covered by the shape of our model. Finally, if you want, you can compute the log likelihood for the one-dimensional dataset as well, and you will get this value. Now, a couple of words on the laboratory part, on the project part. For the project part, we are still doing exploratory analysis. We will still work with univariate Gaussian only. And what we will do is we will try to take each feature. Remember that the first laboratory you were doing what? You were plotting the histograms of the feature of each class. So you were considering each feature independently and plotting the histograms of each feature. So feature 1, then feature 2, and so on. Now we will do the same, but this time we will plot not just the histogram, but also the distribution density of a maximum likelihood model estimated for each feature. So for each feature, we will take class 1 and class 0, build the maximum likelihood one-dimensional Gaussian model for each of the classes, and plot it on top of the histogram. So we take, for example, the first component of the data matrix, we splice into class 1 and class 0, then we compute maximum likelihood for component 1 and variance for component 1 for class 1, then the same thing for class 0 from the component 1 of our data matrix, and then we plot these densities on top of the histogram to see whether one-dimensional Gaussians are good fit for the different features. From what we said today, this would be the solution of a naive Bayes model fitted to the different feature components. we'll see this better next week. But this would be what a naive Bayes model would do. It would fit independently one-dimensional Gaussian to each of the features. So for the moment, it's still an exploratory analysis. So we try to fit the data with Gaussian densities to the data to each feature and compare them to the histogram. We will see that in some cases there will be a good fit, and in some other cases there will not. And this will have consequences when we use this for classification next week. Last word to say is, for the moment we are doing exploratory analysis, so we can compute maximum likelihood estimate using all the samples of the dataset. From next week, we'll create Gaussian models for classification, and in that case, we will do as we did for LDA. We'll take only a subset of the data to learn the maximum likelihood estimates, and then we will use this to make predictions on the other part of the dataset. For this part of the project, you can compute maximum likelihood estimates over the whole dataset, but next week, remember that we will focus only on the model. We will recompute maximum likelihood estimates only on the model training part, because at that point we want to use the data to perform classification. Here we're just trying to figure out how well a Gaussian density would describe our feature. So we don't really need to divide into training and validation, because we are still doing just a qualitative analysis, visual analysis of how good the model would fit our data. Questions? Okay, then you can work, and I will have breakout rooms where I will answer one-to-one questions without disturbing the other people. So if you have questions, just ask, and I will talk to you one-to-one so we can see what's the problem. And don't hesitate to ask, because if you have issues and you don't ask, you remain with the issue. If you have issues and you ask, maybe you will still remain with the issue, but there is hope that I will be able to solve it.